Alrighty, ladies and gentlemen, boys and girls, it's time for another one. Question 2, 2019 AP Calculus AB exam. Let's get to it. So, we see a chart right off the bat before we even start to read. Anytime we see a chart on the FRQ section of the AP Calculus AB exam, we're thinking there's probably a good chance we're going to be asked to do a Riemann sum. So, before I even read what the problem is saying, well, actually, let's read the problem and then go back to that. What the problem is telling us is that the velocity of a particle p moving along the x-axis is given by the differentiable function v sub p, where v sub p of t, let's say that 10 times fast, is measured in meters per hour and t is measured in hours. Selected values of v sub p of t are shown in the table above. Particle p is at the origin, position 0, at time equals 0. Okay, so initial position is 0. So these chart values tell us the velocity of this particle p at these selected values. Just to sort of remind you about velocity, we do see some negative values here. Okay, so velocity is a signed measure, meaning positive means one direction, negative means the other. By convention, we usually say a positive velocity means right or up, and a negative velocity means left or down. Okay, so this particle is moving left and right along a line. We will go ahead before we get started, and in anticipation of a possible Riemann sum, we'll look at these delta x's, or I guess delta t's, that will be the bases of whatever shape we're asked to do our sum with. So this one being 0.3, from 0.3 to 1.7 would be an interval of 1.4. From 1.7 to 2.8, 1.8, and from 2.8 to 4 is an interval of 1.2. Okay, we have an inkling that if we've got a chart, they're probably going to ask us to do some sort of sum, but we will return to that. So, again, this is telling us the velocity of the particle, not the position of the particle, the velocity. Let's jump right in. Question A says, justify, and just to remind you that this is still a calculator problem, so we will be using our graphing utility extensively. Justify why there must be at least one time t for t between 0.3 and 2.8 at which the derivative of v sub p of t, so v sub p prime of t, wow, say that 10 times fast, and stop there, because we just read some magic words and you didn't even know it. Okay, at least one time, closed interval, derivative. Closed interval, derivative, at least one time. These are magic words in AP Calc FRQ land, and they mean mean value theorem. Okay, closed interval, derivative, at least one time, mean value theorem. Okay, so we'll do a quick review in a second of what the mean value theorem is, but that's what this question is asking. Derivative, closed interval, at least one, mean value theorem, MVT. And so we're going to justify why there's at least one time on that closed interval where the derivative of the velocity, which is of course the acceleration of particle p, equals 0 meters per hour per hour. So that's an interesting one because this 0 thing is not necessarily guaranteed by the MVT, but we will see that because of this interval, in this case, it is. So, you're probably thinking, Mr. Smith, I haven't thought about the mean value theorem in many, many moons. So, let's refresh our memory. So this is FRQ number 2 from exam year 2019. This is just going to be some pre-work before we actually start part A. Oh, forgot an important part in the build-up. Sorry about that. There's another magic word here The differentiable part. Okay, the AP test likes to do this sometimes where they just tell you something is differentiable, but we need to read differentiable function and also tell ourselves, oh, differentiability guarantees continuity. Differentiability guarantees continuity, not the other way around. Continuity does not guarantee differentiability. Remember, we could have that a guy, continuous, not differentiable, but differentiability does guarantee continuity. So this is a differentiable and a continuous function, and that will come into play in just a minute. So back to the quick review of the MVT. MVT tells us that, and actually it's going to come into play right now, that if f of x is some continuous differentiable function on some closed interval, then the following is true, that there is some c in that interval such that the derivative of f at c is equal to the secant, or the slope of the secant, of your endpoints. So what? This guy. F of b minus f of a over b minus a. Okay? Visualizing this. Okay, we've got some curve, we've got an A, we've got a B. If you draw the secant line here, because of the continuity and differentiability along this interval, the slope of this secant, given by this expression, is going to match at least one of the slopes, and in this example I just drew, looks like two of them, two of the slopes of our derivative, or of our tangent line on that interval. Okay, there is at least one value c somewhere in this interval where the derivative at c matches that secant. That's the mean value theorem. And we're going to use that to answer part A. Okay, so part A, just to flip back and remind us, the interval we're looking at is the closed interval from 0.3 to 2.8. But before we do that, we need to say because v sub p of t is differentiable, that guarantees continuity. So because it's differentiable, it is also continuous on 0.3 to 2.8. And these are the two conditions we need to in order to use the mean value theorem. And the mean value theorem then will tell us that there is some t value for which v sub p prime is equal to v sub p of our endpoint difference, so v sub p of 2.8 minus v sub p of 0.3 all divided by 2.8 minus 0.3. And we better hope that this difference is 0. So let's go back to our chart. Oh, happy day. Those two function values are the same. This turns into 55 minus 55 divided by 2.5, which is of course 0. And so the mean value theorem guarantees this. Okay? The mean value theorem will guarantee that. So we can say by mean value theorem, or MVT, the AP reader will know what MVT means. By MVT, there is some t in between 2.8 and 0.3 such that v sub p of t, v prime of t is equal to 0. Okay, and that makes sense that if we have this curve that is starting and ending at the same point, okay, this kind of side justification, that if this curve is our v sub t and it starts at 55 and then comes back to 55, either it's sitting at 55 the whole time, where of course that's a derivative of 0, or it needs to turn around at some point, and at that turning point is where our derivative will zero out. Okay, so that was part A. Part B, let's box that up. By MVT, there's some t in there such that a derivative is 0. Okay, part B. Use a trapezoidal sum with 3 subintervals. Oh, trapezoidal sum. Told you it would happen. With 3 subintervals, we have 4. Okay, so we're not going all 4. We're just doing 3. To approximate the value of this integral. We're going to approximate the value with a trapezoidal sum. Wow, got a real lift going on today. So, part B. The integral from 0 to 2.8 of v sub p of t dt can be approximated by the trapezoidal sum. Okay, remember trapezoidal sums calculate the area of a trapezoid, which is half height times base 1 plus base 2, where our bases are actually the function values at each of these guys. Okay, remember these kind of like sideways trapezoids. So we're going to have, for our first trapezoid, our height is the interval, so 0.3. Base 1 is going to be the function value at 0. Let's do this like this. Okay. So 0 plus 55 divided by 2. Our second trapezoid will be, the height will be 1.4. Base 1 is 55. Base 2 is negative 29 divided by 2. And then our third trapezoid has a height of 1.1. And our bases are negative 29 and 55. All that divided by 2. Okay. Now, if this were not the calculator section, I would just leave that answer like that and run for the hills. However, since we do have the calculator, we can actually pop this in real quick and get the actual approximation. And if you do that, you end up with a value of 40.75. 40.75. Now, it didn't ask for units, it just asks for a Riemann sum, which can kind of by nature be unitless. Okay. However, it would be worth our while to think about what does this number represent. Okay. It is tempting to think that this represents the distance traveled, okay, because we are summing up the accumulation of the changes in our position, given by the velocity, those instantaneous changes. And so it's tempting to say, okay, that means in 2.8 seconds, the particle has traveled 40.75 meters. Okay, but that's not exactly true, because consider that we have left and right movement as shown by positive or negative velocities. Okay, so if we're moving positively the whole time, then yeah, sure, that will be the total distance. But we can see that's not the case on our interval. There are times on that interval where we've been shifting left. Okay, and so this number right here actually tells you the position relative to where you started. Okay, so in that 2.8 second interval, wherever you started, you're now 40.75 to the right. If this had come out as a negative number, we would have been to the left of where we started. Okay, so this, and this is not part of the question, but this is going to come up in a second. This integral right here represents position at 2.8 relative to position at 0. Okay, if we wanted the actual total distance traveled, which is what they're going to ask us in just a minute, we would have to take the absolute value. Okay, because even when we're moving left, we're still traveling. The particle is still moved, but this, because it is not accounting for that, is just telling you the position. Okay, if we wanted actual distance, total distance, we'd have to take the absolute value, which we'll do in just a sec. Okay, so part C says, a second particle named Q also moves along the x-axis, so that's velocity, for the closed interval from 0 to 4 is given by the function v sub q of t is equal to 45 times square root of t times cosine of 0.063 t squared meters per hour. It's a friendly function. Find the time interval during which the velocity of particle q is at least 60 miles an hour. Find the distance traveled by particle q. Find the distance traveled. That's where we're going to look at some absolute value there. The distance traveled by particle q during the interval when the velocity of particle q is at least 60 miles an hour. So there's a couple parts here. We first need to look for a time interval. Find the time interval for which this function has a value greater than 60, which would be really hard to do if we didn't have a calculator, but we do have a calculator. Then we're going to use that time interval to find how far does it travel during that interval while it's traveling faster than 60 miles an hour, okay, which will require a definite integral in our calculator, and then that thing we just talked about making it an absolute value so that it actually tracks total distance and not just position relative to the starting point. Okay, so calculator heavy question. We'll jump right in. We'll go to our y equals, we'll clear out the last problem, and we'll enter into y1 this 45 times the square root of t, which we'll call x, times the cosine of 0.063, and then x squared, close parentheses. And we're going to do a second function here because we're going to figure out when is it more than 60. So we want a second y equals 60 function to figure that out. For our window, since we know it's going to be at least 60 on the y-axis, well, the x-axis we know goes from 0 to 4, so let's maybe go 0 to 5. The x-axis, let's go 100, let's say. Let's scale by tens and see how we do. So there's our velocity of q. Real nice. There is our speed limit that we want to go over. And so now we can figure out what these two intersections are, and that will be our interval. So we'll go second trace. We do an intersection. This is our first curve. Second curve. Yes. And that intersection is 1.866 for the second guy. We'll go to the other side. Boom, boom, boom. Call it 3.519. Which both fall within our interval, which is nice, from 0 to 4. Okay, and so that's part 1 of part C, is that we just need to maybe pretty that up a little bit and say the particle Q has a velocity greater than or equal to 60 on the interval between 1.866 to 3.519. So that's going to hopefully score us 1 point. Nope. The next part of the problem was, okay, on that interval, how far does the particle travel? Okay. In that section of time where we're in excess of 60 miles an hour, 60 meters an hour, 60 meters a second, 60 meters an hour. How much travel does the particle do? So that means we want to look at the definite integral on the interval we just figured out, 1.866 to 3.519. Again, since they've given us v sub q of t here, let's just use that notation. But then critically, we want this as an absolute value. We want the absolute value to get that actual distance traveled to account for the fact that this particle might change direction at some point. And it's still accruing distance, but in an integral without the absolute value, that will cancel out. Okay? The negative distance will cancel out because you've dropped below the x-axis, and that area, which is another way to think of this integral, is going to cancel out with the positive area. So we can do this in our calculator. Quite easily, if we've taken care to enter in this information. So I'll go second quit. We will do math 9, the definite integral from 1.866 to 3.519. We've stored our function in y sub 1, but we want to make it an absolute value of that function. So we'll go math num absolute value, option 1. See those absolute value bars? Then we'll go to bars, y bars 1. We are differentiating or integrating this with respect to x. Press enter. And so this is the total distance traveled. 106.109. And our conclusion will be on the interval where the distance traveled by particle Q. And again, if we're ever kind of unsure how to conclude something, steal the language from the problem. We're looking to find the distance traveled by particle Q during the interval when the velocity of particle Q is at least 60 miles an hour. Just copy that verbatim if you're not sure what to say. The distance traveled by particle Q during the interval when the velocity of particle Q is at least 60 meters per hour is 106.109 meters. Units important here. Traveling in meters. That is part C. Okay, so we're almost home free. One to go. So the final part of this question is part D, and it asks us, real quick, at time t equals 0, particle Q is at position x equals negative 90. Okay, that's interesting. Using the result from part B, well, part B was our approximation using a trapezoidal sum, which we said was the position, because it was the signed distance, from part B, and the function v sub q from part C approximate the distance between particles P and Q at time t equals 2.8. So how far apart are these guys at 2.8? Well, from part B, we have an approximation, which we'll use, of where exactly particle P is at 2.8. I think we said that that was like 40.75. We need to figure out where is particle Q at that same time, and then just take the difference. Okay? There's a slight wrinkle with particle Q, because unlike particle P, its initial position is not 0. Okay, so it's tempting to kind of say, okay, we'll just do the same integral for v sub q of t, and then that's our position, but it's not, because our initial position is negative 90. Okay, but we will lay that all out hopefully pretty clearly. So part D, we can say from B, the position of P at t equal 2.8 seconds is 40.75, sorry, not 25, 75. So we need to give the position of particle Q at 2.8 seconds, okay? The position of Q at t equal 2.8 is given by this same integral from 0 to 2.8 of v sub q sub t dt. But again, this is the relative position from this starting point, okay? The position at 2.8 relative to where you were at position 0. With this, we started at position 0, so it was just whatever the answer was, okay? But we need to do this relative to where we were at 0. The problem tells us that at time 0, we were at negative 90. Okay, this is the position at time 0. Okay, we can use the calculator for this. So we go to the calculator, we do a definite integral, math 9 from 0 to 2.8. Oh, I guess you can't see that. There we go. Of bars y1, this time without the absolute value, because here we are looking for position, not total distance traveled, dx. And then whatever this position is, we need to subtract 90. That's our starting position. Taking a minute to think. And it comes out to 45.938, let's call it. Let's go a little farther. 45.93765. So at time equals 2.8, Q is here, P is there, so the distance between them is the difference between those numbers. So 45.93765 minus 40.75. Or if you want to not worry about rounding, just subtract directly from here. 40.75. And our conclusion will be, call this 5.188 meters. Our conclusion is at time t equals 2.8, particle P and particle Q are approximately 5.188 meters apart. Box it up and say sayonara to this problem. Whew, another 30-minute effort. All right. Earning our money here. Okay, so that was FRQ question 2 from the 2019 AP Calculus AB exam. See you later.